I know we're not really focusing on the free response that much, but your free response will be a lot like the one from the spring 22. This is spring 22, last spring. You're going to have a circuit problem that will look a lot like this. I do want you to recognize here this part A. This is something that you'll need to practice. This is where I'm actually solving for t. So just be aware. We did do that in class, but you'll need to practice that where you're solving that exponential function for t. It requires the use of the natural log. Well, we did in class. We didn't do it that many times, but I do want you to do it. It's just sort of the mathematics of working with exponential functions is kind of important. So it'll be a lot like that number 1. I'll give you more details next week, but a lot like number 1. And then probably you're going to have one like this number 3. I'll let y'all know next week. And then, of course, you're also going to have, a multi-loop circuit with a variety of batteries and stuff. So you have a multi-loop circuit, and I'll ask you what is the current in 2 or more of the branches, 2 or 3 of the currents. So that'll be the free response for the exam, which is a week from Friday. But for the quiz, we're looking at the last 5 years of exams. I sent y'all the number of questions from each exam. You have any particular questions about them? Yeah, I can. Oh, she raised her hand. Just a second. We'll come back to you. Why is A correct? So with our junctions, you just pick a junction. Doesn't matter which one. I'm going to pick this one. And something else that I do that often helps me is that I will draw the currents here. So like this is current I1, and this is current I3. Notice that I1 starts right here and goes through up here, goes through there, and goes down there. So even though I draw the arrow for I1 up here, that current is also on this side and on this side. So that is I1, and then similarly I3 goes through that bottom branch. So when I'm looking at this junction, the ingoing currents include I1 plus I3, and the outgoing current is I2. Now if I wrote that equation over here, it would be the incoming would be I2, and it would be equal to I1 plus I3. But of course, those are the same equations. It's just flip-flopped. Do you want to go through the others too? No. Okay. Yeah, the junction rule, do this, where you draw the currents, especially on those that are more complicated, like this, when we're trying to figure out the unknown current. It'll really help you to just remember that those currents aren't just right here, that they're all throughout that branch. Remember when I say branches, just a second, when I say branch of a circuit, I mean this is a branch, this is a branch, and this is a branch. And in this one, I have I1, and this one, I have I2, and in this one, I have I3. I know we also talk about loops, the big loop, the top loop, the bottom loop, but the branches are also important to consider. Joey?
I still just need help in general with a multi-loop circuit.
Okay. Well, we'll do a multi-loop circuit. We'll find some. Dee, you had a question too?
Yeah, I have a question about the volts. How do you know when there should be positive and negative?
Okay, so let's look at multi-loop circuits in general, and then why don't we just do like a free response? I have one here. Yeah, so let's do this one for free response. I'm going to get rid of all this. I have space. I don't know what that was. Oh, that was the free response from last time. So the quiz will be 10 questions as usual, but guess what? You get more time. You get 30 minutes. I don't know that you'll really need that 30 minutes. Most of you probably won't, but you'll have it. All right, so really important to remember the rules. So for batteries, all that matters is the direction that you're traveling. So if I'm going in this direction, my change in potential is positive. I have a positive change in potential. I'm going. Always remember, it's like I'm going. Oh my goodness, what was that? I'm going up, like on the roller coaster, chug, 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 chug. And then if I'm going in the opposite direction, then that means if I'm going in this direction, it's like, oh, I'm losing energy. And so that's a minus change, a negative change in potential. So you need to remember that. And then with resistors, you have two rules as well. And in this case, two things are important: the direction of the current and the direction that you're traveling. In this case, if I'm going with the current, then the change in potential is negative IR. That's what resistors do. They cause a drop in potential. And so when I'm going with the current, the resistor does what you would expect it to do. If I'm going against the current, just so I know that's separate. If I'm going against the current, so the current is in this direction, but I'm going the opposite direction, then that change in potential is positive IR. Okay? So the first thing you do when you come to a circuit is you pick the direction of the currents. I've already labeled them here, but I would pick the direction. Doesn't matter what direction I pick. I just don't think about it, just pick left or right. And again, though, when I draw this, I say left or right, but really it's going up here, left, and then down. But I just use that left, right just to, as a notation. But there really is a current through that entire branch. Pick the direction for the currents. Then I'm going to write loop rules. Now, it matters what loop you pick. You want to pick loops that will make the math a lot easier for you. And I usually give you loops that will make it easier. What you want to look for is a loop with no resistors in it. Because if I have a loop with no resistors, that means I have that current is not in that equation. That means I have one fewer unknowns. So pick a loop without a resistor in one of the branches. So for example here, I might do the bottom loop and the big loop. Let's write the bottom loop first. In the bottom loop, I pick a point to start. I'm going to start right here. Doesn't really matter which way I go. I'm going to go this way. I come to the 8 volt. Is that plus or minus 8 volts? I'm going from big to little. So it's negative 8 volts. Actually, I'm going to leave this volts off and just write the variables, not the units. So I have minus 8. I'm going, covered up my direction. What was my direction here? No, it's the same, yeah. So then across that resistor, is it plus or minus? I'm going with the current, so it's minus 5. And then the other important thing is I get the current labeled correctly. So it's going to be minus 5 I2. Then I'm going to do the bottom loop, so I come down here and I have plus 2 is equal to 0. All right? So I can solve this for I2. Let's go ahead and do it. I have minus 6 minus 5 I2 equals 0. So I2 is equal to 6 divided by negative 5, negative 6/5 amps. So I can write the answer for that. Well, let's not right now. We'll just go ahead and write the big loop now. Isn't that right? We're going to do the big loop. Why am I doing the big loop and not the top loop? Right, because the big loop has one branch that doesn't have any resistors. But notice if I did the top loop, I would have 2 unknowns. It wouldn't be that difficult because I actually now know one of those unknowns. I know I2. But I'm going to write the big loop. It makes my math a little bit easier. So the big loop, well, let's start right here. We'll go in this direction. That's going to be plus 2. Coming up here, what across this 2 ohm resistor? Is it plus or minus? Notice my current is going in that direction. It's going to be plus 2 times the current, and that current is I1. Remember, that current flows through that entire branch. So be careful when you're going from one branch to another that you realize the transition in the current. That whenever I cross a junction, now I've got a new current that I'm dealing with. So plus 2 I1, plus or minus 3? Minus 3, and then that's it. It comes back to where I started. That's equal to 0. I can solve this for I1. That's 2 I1 equals negative 3 plus 2, that's negative 1, so equal to 1. So I1 is equal to 1/2 amps. All right, so now I've written 2 loops. Now in order to find that third current, I have to write a junction rule. So I'm going to write a junction right here. Just like I did before, I'm going to write my arrows. So they're like this. This is I1, I2, I3. So my incoming current is I2. Outgoing currents are I1 and I3. I'm looking for I3. So I3 is equal to I2 minus I1. That's going to be negative 6/5 minus 1/2, which is negative, what's that, 12 tenths and 5 tenths, negative 17 tenths, negative 1.7 amps. Now I can report my values. I1 is 1/2 amp. Because it's positive, I1 is the direction that I chose it to be, so it's going to be to the left. I2 is 6/5 amps. But notice it's negative, so that means that this direction that I chose for I2 is incorrect. I chose it to the right, that means it's actually to the left. And then I3 is 1.7 amps, or 17 tenths, 1.7 amps. It's negative, so the direction should be what? To the right, opposite of what I chose it to be. That's going to be like your free response next Friday, but also you'll see 1 or 2 questions about multi-loop circuits on the quiz tomorrow too. Yeah.
So, how did you know that 1.7 was going to be to the right? Like, how did you know you had to change?
Because 1.7 came out to be negative right here, and if any of your values come out negative, it means you chose the direction incorrectly.
So you always have to do the opposite when negative comes out.
Right. However, beware that, notice right here, I kept the negative when I calculated I3. You only change those signs when you're reporting the values. You have to maintain the signs when you're calculating the other values, because just to be self-consistent with the equations that you've written. Even though your directions are incorrect, you've written the equations with assumption of that incorrect direction, so you have to keep that assumption until the very end, and then you just take the opposite of what you found for the direction if it's negative. So that's multi-loop circuits. I mean, there's really no trick to them. That's sort of what they are. I mean, I can have different numbers, and you might use different loops and what have you, but that's what they are. Does that help a little bit? Need practice with it, as with all things. Practice is really important.
Can you do spring 25?
Exam what?
Spring 20, exam 3.
Spring 25 has not yet occurred. Spring,
Exam 3, spring 20, number 5.
oh, okay. Spring, exam 3, spring 20. Number 5. Well, that's big. It's so big. Just gonna make it smaller. I think, was this when we were in the pandemic? Yeah, that's why it's so big, because it was, I had it as an online exam. Yeah, it's small. I know. That's okay, right? Can y'all see that? Yeah. All right. So what is the magnitude and direction of I2? So here, on the multiple choice, I have to give you the directions of the currents. Well, I guess I don't have to, but I usually do. And I want to know what is the magnitude and direction of I2. Well, first, I just want to pick the best loop. Usually there's a good loop that'll make this really easy. That's going to be the bottom loop. Why did I choose the bottom loop? Right. More particularly, there's no resistor in this branch of the circuit. That means that I3 will not be in that equation. Now I can pick a point to start. I'm going to start right here. We'll go in this direction. I have 6 minus 6i2 minus 10 is equal to 0. And I solved that for I2. Negative 4 minus 6i2 equals 0. I2 is equal to 4 over negative 6, or negative 2/3, or negative 0.67. So it should be 0.67. And notice I chose I2, or I was told I2 is to the left, but it's really to the right. So D is the right answer, 0.67 amps to the right. Okay, so that's just like a piece of that original free response problem that we had. Good news is that there aren't that many multi-loop circuits like this in the multiple choice part. That's past few years I've been doing most of that in the free response. So there aren't that many questions of those for you to practice.
Is not what we pick, it's the current. Like, there's the current's running one way, but when we solve, we pick a direction to go in.
Yeah, there are two.
Based off of the actual current direction.
No, I can choose any direction. Like I could have chosen to go this direction, and it would have been minus 6 plus 10. What's that? I'm going against the current, so plus 6 I2.
I'm saying like when you do the answers like to the right, it's not based off of you chose to go to the right, so you flip it. It's based off of the current.
Yeah, it's based off of the current direction, not your traveling direction. Is that what you're asking? Yeah. Yeah, so the traveling direction is separate. In fact, the traveling direction doesn't even really matter. Notice here, I wrote this equation with a different traveling direction. But if you'll notice, that's the same as this equation. It's just the negative of it, right? The 6 is negative, the 6i2 and the 10 are now positive. I've just took the negative of that equation. So those are the exact same equations. It doesn't matter the traveling direction. It doesn't matter the direction of the current either, as long as you're consistent in it. Okay? What else? Are y'all okay with RC circuits? Oh, look, I have a seminar on Monday. So with RC circuits, there are 3 types of problems that you'll see. One of them will be, tell me what is the current, the voltage, or the charge for a particular circuit, in which case you'll have to use one of these equations. All right, and we'll do one of those. It's really just knowing which equation to use, using the right values for R and C and Q and T, and then plugging it in correctly. I want you to know how to manipulate and how to work with an exponential function, because exponential functions are they're important. They come up in a lot of different places, and this is just one of those places. The other thing that you'll need to know is you'll need to know how to find the time constant. That's called the time constant. And also, you need to know how much time to fully charge or discharge. Now, beware that I'll ask both, and sometimes they look similar. They both have time in it, but they're different. So the time constant is equal to the resistance times the capacitance. Tau is equal to RC. But the time to fully charge or discharge is equal to 10 tau, right? 10 times the time constant. So if I'm looking at, say, a graph of the charge versus time for a charging capacitor, initially the charge is 0. After 10 tau, a time equal to 10 times the time constant, that capacitor will be fully charged. It will have reached its maximum value. At a time of tau, it's at about, I think it's 67% of the maximum value. So that time constant is not the time to fully charge. It's not even time for it to be halfway charged. It's really just sort of a characteristic time that describes that exponential function. And in this case, that time constant is equal to RC. But in other cases, your time constant might be some other, like if you're looking at, I don't know, population growth or decline or whatever, that time constant is given by some other constant. But in this case, it's RC. And then the third thing that you need to know is I'll ask you for a charging or discharging capacitor to describe or to show the graph that describes that circuit. And that graph will either look like a growth function or a decay function. A decay function mathematically looks like this, e to the minus t over rc. That is a decay function. In fact, as t gets bigger, this function approaches 0. The limit as t approaches infinity for that function is that function approaches 0. Y'all remember limits from calculus? Y'all did limits? You did. In calculus? No, you don't. Okay, well, as you know, since it's a negative exponent, it's in the denominator. As that denominator gets big, it goes to 0. On this one, though, this is 1 minus e to the minus t over rc. And as time gets bigger on this, it approaches a value equal to 1. So this function approaches a value equal to 1. Or if I see it in these equations, it approaches q, or it approaches the maximum v, or it approaches the maximum current. It approaches whatever value is the coefficient to that exponential function. Let me show you what that looks like on the exams. Those 3 types of problems. So here, number 7 is like that most recent one. Let's blow this up just a little bit. So I think this is spring 20. I need to first ask, is it charging or discharging? I have a current versus time after this switch is closed. So initially, it doesn't have any charge, or there's no current flowing, but if I close this switch, then I get charge that flows through this circuit and begins to put charges on this capacitor. So this is a charging capacitor. And I want to know which of these describes the current. Let's go back and look at the equation sheet. So the current for a charging capacitor looks like this. In fact, the current for a charging and a discharging capacitor will look the same. You'll initially have a big spike, and then the current goes down. So that is going to be the answer. It will look like A. A is the right answer for that one.
How do you know what equation goes to the capacitor or resistor?
Well, because I want to know the current. I'm looking for the current. So when I go back to my equation sheet, my current is right here. So that's how I know that equation. And then I'm also looking for a charging capacitor. So it's going to be that one, since that one says that it's charging. You can think about it physically too, that when I hook up that circuit, that initially, since there's no charge on the capacitor, I'm going to get a big burst of current, an initially big current that will begin to fill that capacitor. But as that capacitor fills, I don't need as much current to fill it up, and so that current declines or decays with time by that exponential decay function. It looks like this. So you need to determine, is it charging or discharging? And then what am I looking for? Voltage, charge, or current? And then come here and ask, all right, which of these functions describes that situation? Okay? So really you just need to remember these, and then you'll have the equation sheet to apply to whatever situation you have. Practice that. It's not hard, it requires practice. The others, here you have to calculate the charge. Again, is this charging or discharging? Well, it says it initially has no charge, so that means that it's charging. Let's go back and look at that equation sheet. For a charging capacitor, I can calculate Q by that equation. So I know that Q is equal to big Q times 1 minus e to the minus t over RC, or tau. Q here is the maximum charge on that capacitor, and it's equal to C times V. So that's 5 times 10, or 50 microcoulombs. So I have Q is equal to 50 times 1 minus e to the minus t, which is 5, that's given, and then RC which is 1 times 5, or 5 seconds. And then I calculate that. You might just want to double check that you know how to do that on your calculator. If you haven't done it, just try it out. 1 minus, e is usually second natural log, e to the minus, well here I'm doing minus 1. I get 32. So 32 microcoulombs. Oh, the answer is 30 here. I didn't keep the proper number of sig figs. I really should have reported 32 in the answers, but the answer is 30. Okay? So that's another type of problem. And then the third type of problem, let's see if there's one here. Here, like number 1, this is spring 21. What is the time constant? That's asking tau. I know that it's tau because it says time constant. I'm looking for that. So it's just going to be 2 times 5, which is 10 seconds. Notice that the micro, which is 10 to the minus 6, and the mega, which is 10 to the positive 6, that those both go away. So I didn't even bother dealing with those metric prefixes. And then the other thing that I might ask is, how long does this one take to fully charge or discharge? Well, that would be 10 times tau, which would be 100 seconds. All right? What else we got, y'all? Is that all? Yeah.
I don't know, like, where it would be, but, so the problems that are in like number 4, where it's something about, like, someone's installing a circuit breaker, and then it gives you all the things, and it's like, how many, what is the amps that you can put? I was doing one, and it was like, I got my answer that I got wasn't like the answers that were given, and it's something like, you gotta put, like, he's gotta have more than what you saw.
Yeah, let's just, like, we'll do this one, number 4, and I'll make it into that type of problem. So here, I have these devices on a circuit. And remember, I know current is power over voltage. So for example, for the heater, which is 1200 watts over 120 volts, that's what we always have in our home. That's equal to 10 amps. So this heater pulls 10 amps of current. This one pulls 5 amps. That's just 600 divided by 120. That's equal to 5. Here, 120 divided by 120. That's 1 amp. So I have 10 plus 5 plus 1 is equal to 16 amps. So that was the answer to this one, 16. But then let's say that I add, I don't know, a 2400 watt, or no, a 600, I add a 600 watt toaster or whatever. I add that. That means that my current has now gone from 16 to 21 amps. And somewhere in that, or when I add that 600 watt, it kicks the circuit breaker off. Y'all done that before, where you turn on a toaster and the circuit breaker kicks off? Maybe you have. Should have. Maybe. I don't know. So somewhere between 16 and 21 amps is where my limit is. So you would have to look through the answers. They might be 14, 15, 18, 23, and pick a number that is in between 16 and 21. In this case, that would be 18 amps. It wouldn't be equal to 16. It wouldn't be equal to 21. The limit for your circuit breaker, which checks that your current is not more than some maximum value, that limit would be 18 amps in this case. Okay? You'll probably see questions like that too. Oh.
How would you calculate the circuit breaker problems? Like, how would you calculate? I'm trying to figure out what problem.
Well, I like this one. This is number 2 on spring 20. Here I have, remember, P is equal to V over I. So this is 10 amps. This is 0.5, oh no, 2 amps, excuse me, 2 amps. This is that right? 0.5. Yeah, I got this wrong. I is equal to P over V. So yeah, 60 over 120, that's 0.5. And here, 240 over 120, that's 2 amps. So I have 10 plus 2 plus 0.5 is equal to 12.5. And then I add this 180 watt blender, which is, why did I give you all these numbers? What is it, 1.5? I add 1.5, and that's 14 amps. So somewhere between 12 and a half and 14 amps, which is 13, that's where it kicks off. That's where the circuit breaker kicks off. Okay?
We don't have to do any like big calculations for that.
No, just like this. I mean, for the quiz, you know what the questions are going to be. There's no secret there. So whatever's on the old test, that's your questions. Is that all?